Chemistry in its Element podcast. Curious tales of chemical compounds.
This week, Katrina Kramer with an anaesthetic gas that exploded into surgeries, perhaps a little too literally, in the 1930s.
We were doing a perfectly routine, almost minor operation on a woman requiring diathermy, surgery using electrically induced heat, to remove a non-malignant tumour of the tongue. Then the catastrophe occurred. We found ourselves lying on the floor, dazed, and our ears ringing from a tremendous explosion. We were completely deafened. We were also blinded, I suppose, by the flash, but also by the debris in the air. There was a terrible, acrid smell. I remember the smell particularly. I suppose it was the burning rubber of the tube, which connected the patient to the anaesthetic machine.
Those were the words of junior house surgeon A. Friedman, related to Alan MacDonald and published in a 1994 paper in the British Journal of Anaesthesia. The scene they describe did not unfold during a world war. The explosion was not caused by a bomb, but by the very substance that was supposed to keep the patient in a painless slumber during the invasive procedure, cyclopropane. In 1957, when this blast occurred, cyclopropane was a common anesthetic. The compound had been discovered back in 1881 by Austrian chemist August Freund, who initially named it trimethylene.
Freund developed a technique to synthesize cyclopropane using a reaction mechanism known as Wurtz coupling. In this reaction, Freund treated 1,3-dibromopropane, an organic compound with 2 bromine atoms, with sodium metal. This reaction resulted in cyclopropane and sodium bromide being formed. 6 years later, another scientist by the name of Gustavsson improved this reaction by replacing the sodium with zinc. Freund discussed his findings with his original Wurtz coupling reaction in a paper.
Out of the 11-page manuscript describing the discovery, Freund spent 8 painstakingly discerning cyclopropane structure. Without access to spectroscopy at the time, he uses a mix of experiment and detective work that would make Sherlock Holmes proud, concluding the substance must have 3 CH2 units arranged in a triangle, and he was right. The cyclopropane ring is the smallest possible carbocycle. It is, in fact, so small that the chemical bonds get distorted into a decidedly uncomfortable shape. Usually, when there's a single bond between 2 carbon atoms, the bonding electrons sit right in between the 2 atoms. A situation that's represented quite well by the straight lines and structure drawings. Not so in cyclopropane. Intense strain warps the carbon-carbon connections into what chemists call banana bonds, an apt description of the bent electron clouds that look like they're on the verge of breaking apart.
These banana bonds are caused by angle strain within the cyclopropane molecule, a type of strain that is present in all cycloalkanes. This is because when a carbon atom covalently bonds with 4 other atoms, it assumes a trigonal pyramidal electron geometry, since its bonding orbitals hybridize to form 4 sp3 orbitals. These sp3 orbitals are at 109.5 degree angles with one another in regular carbon bonds. Typically, a covalent carbon bond in an sp3 configuration will have its bonding orbitals overlap linearly with the bonding orbitals of the atoms it is sharing electrons with, creating a strong sigma bond. In cyclopropane, however, since each carbon atom is forced to bond with 2 other carbon atoms in a triangle, the sp3 orbitals do not overlap linearly, but rather only near the edges. This reduced overlap between bonding orbitals causes the carbon-carbon bonds to be weaker than normal, with bond enthalpies going from 370 kilojoules per mole in a regular carbon-carbon bond to 255 kilojoules per mole in these banana bonds. Another factor contributing to the weakness and volatility of the cyclopropane molecule is torsional strain. Torsional strain occurs in a molecule when single bonds are not allowed to rotate freely due to eclipsing bonding groups, which are just bonding groups on 2 bonded atoms that repel each other in a way that prevents free rotation of the bonding atoms. In cyclopropane, the CH bonds eclipse each other and inhibit rotational movement within the carbon-carbon bonds. This creates additional strain on top of the angular strain, which is also known as ring strain, from the banana bonds. These two strains within the molecule are what cause it to be so reactive. The carbon atoms want to be unconstrained both rotationally and angularly, and will thus react relatively easily to form more stable compounds.
So it might not be surprising that cyclopropane is quite reactive and prone to exploding when mixed with oxygen and a spark. That didn't keep scientists from trying it out as an anesthetic. In the early 20th century, doctors were looking to replace ether. Although this had been the primary anesthetic for more than 50 years, it had side effects, causing nausea and vomiting after surgery. In 1928, two Canadian physicians started to test cyclopropane on animals. Once they got the mixture right, around 10% with air, it turned out to be quite successful. A cat placed in a tank filled with a gas passed out within a few minutes and, according to the researchers,
did not respond to poking.
Once removed from the tank,
the cat winked and moved its tongue in 1 minute, sat up, and walked about in 3 minutes. In 5 minutes, purred when petted. It was quite normal a week later.
They also tried the gas on a
very fat
2.5 kilo rabbit. They anesthetized it 3 times in a row without apparent adverse effect. By the mid-1930s, cyclopropane was produced industrially, giving doctors access to the gas in large quantities and of high quality. It turned out to be a potent anesthetic, not only for cats and fat rabbits, but also for humans. People recovered quickly from cyclopropane-induced anesthesia, and its sweet smell meant inhaling it wasn't entirely unpleasant. But cyclopropane's increasing popularity meant more people started to experience its explosive side. In 1939, there were 74 cyclopropane explosions in US operating theaters, 13 of which were fatal. Nevertheless, as MacDonald pointed out in 1994,
although many causative factors were identified, no lessons appear to have been learned, as fatal explosions continue to occur every year.
Among the causes were sparks caused by static electricity, power plugs, and switches on lamps and surgical equipment. In one particularly gruesome accident, an entire cyclopropane cylinder exploded during an operation, flinging shrapnel and igniting several other gas cylinders in the same room. The patients, 2 children operated on simultaneously, and 4 doctors were killed, 2 nurses and another doctor mutilated. An investigation found that the cyclopropane cylinder had been partially filled with oxygen by accident before cyclopropane was added. Gas cylinders are often reused in hospitals, but this time the practice of using the same cylinder for different gases produced a deadly mixture. As cyclopropane's use in the operating theatre increased, so did research into its side effects. After prolonged periods of unconsciousness, some patients collapsed as their blood pressure dropped rapidly and their heartbeat became irregular. This so-called cyclopropane shock eventually marked the demise of the triangular molecule as an anesthetic, probably for the better of everyone involved. Today, fluorinated ethers are the most widely used volatile anesthetics. Although cyclopropane caused many fatalities in a place that was supposed to heal people, the junior surgeon from the beginning of our story got away unharmed.
To everyone's astonishment who hears this story, the patient survived.
Katrina Kramer, ably abetted by the Chemistry World team. Next week, Brian Clegg returns with a twinkle in his eye.
Zircon's use in jewellery gives us a window into human history, but the crystals also act as time machines, giving scientists insights into the chemistry of the early Earth.
Join Brian next time. And until then, the usual lines of communication are open. Email chemistryworld@rsc.org or tweet @chemistryworld. I'm Ben Valsler. Thank you for joining me.
chemistry in its element. For more podcasts, as well as the latest news, reviews, features and opinions from across the chemistry community, join us at chemistryworld.org.